see how this first one here, this is going to be straight lines because the slope is constant in those regions. Here, is the slope constant in this region? It's going to have to be curved. Here will be a straight line here because the slope is constant, but out here they're going to be curved lines. Oh shit. So let's go back. Let's do number 1. Let's see. So what's the first places you locate for this one? What do you find first? Zeros. I like it. You guys are, I love you guys. I know the answer, I just don't want to say it for some reason. So about right there, roughly. Make your points big, then you're safe. Now what's true about the slope back here? What's true about the slope here? Really big positive, right? And then it's getting less and less positive. It's really big positive, getting less and less positive. And of course, what happens to the slope in here? It's negative, getting more negative, and somewhere in here, it's the biggest negative, and it's going to be, and then it gets less negative. So I'm going to put it right here just because. Somewhere in here is that point where it's the most negative it's going to be, and then it starts to be less and less negative, and it's exactly that point is where it's the most negative. And then it gets less and less negative, and then what happens after here? Yeah, after this point it's positive, getting more and more positive. So what kind of function is this? The original function, what kind of function is it? Somebody, from the shape of it, it's x to the third. Right? It's related to x to the third with that other shit in the middle to make it get all freaky in the middle here, right? And the derivative of that looks like it's related to x squared. So that's that idea of when you take the derivative of a polynomial, the power gets 1 smaller. If you do enough of these shapes, you start to go, well, shit, yeah. Here's an x to the 4th, and when you graph it out, it's going to be x to the 3rd. That's going to be the shape of it. And the algebra of the calculus that we are going to do eventually is going to actually bear that out. Yes, it does become that. It does go down by a degree. Yes?
How did you know what that bottom point is?
Oh, I just eyeballed it. That could shift a little bit for everybody, but that to me looked to be about the place where it was the most negative. But really, what do you have to do? You got to be 0 at -3, and they got to somehow swing back around so you can be 0 at 3 again. So your bottom could be in a different little place, but that's why I put mine there, is because it looked to me like that was where it was the most negative. I'm trying to make a big deal out of that because the inflection points are going to become very important to us later. What about this dude? Straight lines, so they're both easy. What's the slope back here? -1, right? Alright, so it's -1 all the way through here. And what is it over here? It's 1 all the way through there, but right at 0, it's nothing. It's not differentiable at 0. I like to point at that's a plane I don't want to be on. We're flying, and then bam, we're suddenly flying that way. We are all slammed up against the wall, dead, all flat. Our plane's probably dead too. I don't. If you don't like that image, okay, I'm sorry. So this is going to help you out with the next one. There are 3 places on the next one that's not differentiable. It's not differentiable somewhere where the derivative function itself would be discontinuous. So at what we call a cusp or a corner, depending on if you've heard those terms before, that's what I would call a cusp. That is, or a cusp really is like this, but that's where it turns a corner. It's got a kink in it. So the slope itself is not continuous. So I'd say it's not differentiable there. If I zoomed in at 0, would it become linear? It would just always be a little triangle, wouldn't it? Just a little corner. I don't care how much I zoom in on it. It's never going to become flat. It's never going to become straight. And if it is differentiable, it has to. Because that's what the derivative means, it means that's the slope of what it looks like when you zoom in a lot. Well, that's not going to look like shit. It's just going to always look like, it's not going to look like a straight line. It's going to look like this forever if I zoom in. All right? I can show you what it doesn't. So down here, where's an obvious place then this is not differentiable related to what we just did? Yeah, -2. So an x equal -2. There's this corner. Where else? At 1, there's another kind of corner. Not as sharp of a corner, but still it would kill us all. That's a place to avoid. And then one more really kind of in-your-face obvious place.
This
3. So here's a theorem for you. If a function is differentiable at a point, then it must be continuous at that point. People do not understand the if-then. Let me ask you something. Let me say this. So just to talk about if-then real quick. Because you're going to see a lot of theorems in this class. And if-then is so flippin' misunderstood. If I told you, this is very hypothetical. Don't get all excited. If I said, if you make an A in this class, then I will buy you a car. I love people that you wrote. Yeah, little Matilda. Here you go. If you make an A in this class, then I will buy you a car. So let's say you make a B. Am I going to buy you a car? I could. I could if I wanted to. This is what's not understood. If you make an A, then I will buy you a car. If I don't buy you a car, you must not have made an A. That's the only way that works. If A, then B. If not B, then not A. If you make an A, then I'll buy you a car. Could I buy a car just because I want to? If you stop breathing for long enough, you will die. Then you will die, right? If you stop breathing for long enough, then you will die. So if you breathe for long enough, then you will never die. Is that true? You could have a piano fall on you. And then you're dead. You're breathing up until that point, just fine. Boom, and flat. Again, there's a big theme today about flat people somewhere, but so the if-then statement is so misunderstood. It's a little contract. If you make an A, then I'll buy you a car. I made an A minus. I'll still get you a car. If you don't meet your first part of it, I can do whatever the shit I want to. Right? Maybe. So if you do breathe forever, you could still die. You just are not going to die because of not breathing. Right? Maybe. So the if-then statement is, every time we hit a theorem, I'm going to try to show you again how not to look at it. Right? You can't consider just negating both parts of it and saying that's true. That's not the way it works. Okay. So here it's not continuous. So if f is differentiable at A, then f is continuous at A. So if f is not continuous at A, then it must not be differentiable at A. It's like if I don't buy you a car, then you must not have made an A. That kind of, you can turn it around and negate it. That's the only other way it works. So here, where is it not continuous? At 3. So it wasn't differentiable at 3. But can a function be continuous and not differentiable all freaking day long? It's continuous here, isn't it? The limits agree and it actually gets to that point, but it's not differentiable. Like that. So it's a misapplication of logic that makes theorems so difficult for some students. Okay. What about this guy? Now the line I draw, the purple thing I'm drawing right now, does it have to be continuous? What's the only information this tells me? The slope through those points has to be a constant 3. So that's got to be continuous on that region. But the minute now I could start from that point at 4. I could keep going from that point, or I could go somewhere else. All I know is that in the next region, -2 to 1, the slope has to be what? 0. Personally, I would go ahead and just keep going from where I stepped. Where I stepped. So I stopped here. I would keep going, but I could jump around if I wanted to. So I'm going to just make it flat here. It's got to be flat. It's got to be 0 slope. And then what's got to be true about the slope? -2, so down 2 over 1, down 2 over 1. And then what's got to be true about the slope? 1. Up 1 over 1. There. So that's one possible answer. Yours doesn't have to be connected if you don't want it to be. I could have taken that flat piece on top that goes through 4, I could have put that anywhere I wanted to, and it would have still been an that's why I say sketch a possible function. There's really an infinite number of answers here, depending on how far you want to take your graph. Maybe. Do you see how my result, is it continuous or not? That purple line, is it continuous? Totally. Is it differentiable throughout? Hell no. At those little corners, it's not differentiable. And I can see that because the derivative itself is not continuous through those points. So what about this dude? So you can kind of do the opposite of what we do. What's the first thing we look for when we're doing this number 1? We look for where it's flat. And that's where we put 0. Now here, it's going to be flat throughout. I mean, where's it going to be flat? You got to be careful. Where's the slope 0? What specific things? At -3 and at 3. What's true about the slope back here before you get to this point? The slope, be careful. What's the slope at -5? 1. This is G prime. So the slope at -3 is 0. The slope at -5 is 1. So see how I can put my starting point anywhere I want to. Because all I have information about is how it's moving, not where it is. That's a little bit like physics. Not being a certain person. So I can start wherever. I'm going to start right here just because. And now I want to go up by 1, but immediately when I move, what happens to the slope? It's getting... Does everybody see the slope right here is 1? Is that cool? So I start moving in the direction of 1, but what's the minute I start to move, my slope gets smaller and smaller. So I'm going to start going up like this, but I'm going to immediately turn. My slope is getting smaller. It should be 0 here. And then over here, it's going to get negative now. Up to this point right here. So positive, 0, negative. Now what's happening from -1 to 2, the slope is there's a constant -1, so down 1 over 1, down 1 over 1, down 1 over 1. So it's a constant, so it should be a straight line, slope of -1. And then what's happening is this is basically the same thing as this, just in the reverse. The slope here is on average, sure. It's negative, but it's getting more positive. What's happening right at 3? The slope is 0, so it should be flat here. And then what's happening? It's getting more positive, so I don't need you to be too precise. I guess I should stop it. That is definitely weird, especially after you do number 1. This is what I call shifting gears. Number 1 is thinking this way, and number 2 is thinking the reverse. And I can hear the gears grinding and see the smoke. I don't blame you for that. It's not the easiest thing in the world. Any questions on that worksheet? I don't think I put a problem like this on the practice test because you just forgot to Frankenstein that in. But this will definitely be on the test. There's quite a few of these in the homework for you to do in section 2.8. This given a graph f prime. Given a function, graph f prime. That kind of problem. Everybody got a practice test, right? Okay. I feel pretty good about that. Get in out early again, unless you guys have questions. It's up to you. Yes. Yeah, let's do that. And if you have stuff to turn in, just bring them up here.
Yeah, can you do 54 on 2.5?
54.25. Oh, okay. Let me show you something. This is the one that's using intermediate value theorem. There's a really cool thing your calculator does that's related to intermediate value theorem when you're trying to find the root of something. Let me show you this and then I'll actually show you how to get that started. So if I put in here a function, that's a funky function. Let's just put in your, let's check 5x minus 2. Wow, I'm going to freaky. Zoom 6 takes you back to standard. So say I'm going to try to find this 0 here. So say second calc 0. That's how you find x-intercepts. Now I'm going to make a mistake. Here's the left bound. Here's the right bound. Here's my guess. Let's see if I can make it do it. Yeah, see that says no sign change, right? Okay, so you're like, ooh, and people at home, you missed that entirely. It's too bad. That no sign change. So if there's going to be a root somewhere, an x-intercept for a continuous function, what must happen right around that root? What could happen? Let me say it that way. If you have a function and it's moving along, what's going to happen a lot of the time for there to be a root? Not all the time.
Square root or like
If over here it's here, and if over here it's here, and it's continuous, what must have happened in the middle? It must have gone through 0. It must have gone through 0. So if I do know that it's positive on one side of something and negative on the other side of something, or let's say a range, there must be an intercept in there somewhere. That actually is intermediate value theorem, because remember what that says is if you're f of a and f of b, you must take on every value in between if you're continuous. Therefore, you must take on the value of 0. There must be a root there. So how does that translate into actually doing a problem? Well, they're going to give you a function, and they're going to say, show that between a and b there's a root. Well, look at f of a, look at f of b, and make sure that the sign changes. Here's the calculator's going, there's no sign change, dude. There's not going to be an intercept in there. Now, does there always have to be a sign change for there to be a root? No, I can stay positive, right? That's where the calculator actually has some trouble with certain functions like this. It has some trouble with that. So, again, what did I say? To show that the root exists within some interval, you do f of one side, f of the other side, and show that the sign changes. Then there must be at least one root. There could be an infinite number of roots, right? But there's at least one. Is that decent? So that's number 54 in 2.5? Yeah. So they give you a function and they ask you to show there's a root. Now, to help you out a little bit, they give you this. I think it's that. For this interval. So what's the f of x you're going to work with? Pull everything to one side. See how that's now saying equal to 0? Do you see this? So then what's your f of x? This. Show that f of 2 and f of 3 have different signs. Therefore, it must have an answer somewhere between 2 and 3. How do I know it's continuous? I'm not assuming anything. At this point, we know it's continuous. Logarithmic, radical, polynomial functions are all continuous on their domain. And 2, 3 works, all those points work for everything. This has only got a problem at 0. And below, this has got a problem below 0. Good point, though. I love it. Don't assume shit. The first thing they should have said is, why are you allowed to use the intermediate value theorem? Well, what's a huge part of it to work? The function you're working with is continuous. If it wasn't continuous, it could just go, ha-ha, transport, ha-ha. So that's why it's got to be continuous for this thing to work. Yes?
Can I ask about the number?
Which one?
It is 61 on 2.4.
2.4?
2.3.
2.3.
I just don't understand what the proof there means, because it was one lesson before the precise definition of the limit, so how are we proving without epsilon delta?
So, look back to see what it means for a limit to exist. That means from both directions it's got to agree, right? That's really almost all we know at that point before we get to 2.4. This one is really neat because you have rational, x is rational, it's 0. I'm sorry, x squared. And if x is irrational, it's 0. So let me try to help just a little bit. This is towards the end. This is what I consider almost my bonus questions. If these are the only questions you have trouble with, you're doing really well. This one and the next two are a little bit freaky, because I think I also assigned... Yes?
64 is like weird.
Oh, that one's actually not as bad as you think. Thanks, Jeff, for making me feel so good. Here's the idea. This is really strange, because between any two rational numbers, how many irrational numbers are there? So between like 0.2 and 0.3, those are both rational, right? How many irrational numbers are between those two? Infinite number. 0.201, 0.202, 0.203. And what I mean is the limit as the place goes to infinitely. In the infinite decimal place, put a 1. Now put a 2. Oh shit, so there's an infinite number of irrationals in between these two. There's also an infinite number of rationals, so it's like, holy shit. The key thing here to realize is, what's the limit as x goes to 0 of this? 0. So you've got, this is always 0 if it's irrational. This is x squared if x is rational. But what is x squared itself going to? 0. So try to put that together into a little, really you just need a couple sentences to get that together. This gets into something called real analysis if you take it that far, but we're not going to take it that far. This is like two separate sequences. The sequence is different if it's irrational versus rational. Right?
Could you plug in 0 because 0 is positive and is that different?
Say again?
Could you plug in 0 because 0 is positive into x squared? Because 0 is rational.
0 is rational, yes.
So you can just plug it in and show
So the fact that the limit of this is the same as the limit of this, that gives you what that limit is going to be. That's why it's going to be the limit is 0.
Oh, I see.
But you just have to put that together. That's it. Yeah. It's not as weird as it sounds when you first look at it. Now if I put in x squared plus 1 here, and I ask you what's the limit, that definitely gets weird. Anything else from homework? Guys? I think the rest of you are just hanging out to see what happens. Yes?
From 2.6.
Which one? 24?
Yeah.
Oh, so remember what is the effective degree of the top of that?
Well, I guess I just was confused on how the square root played in.
Oh,
Or it ended up being like x to the third or something. Obviously, but the way the example I was like looking after, because I didn't know how to do it, the coefficients, I didn't know how it came up with the coefficients that it got.
so if you go back to the most basic way to look at these, no shortcuts. You divide the top and bottom by the highest degree you see. There is no x to the 6th here. There really is the square root of x to the 6th. So you can divide top and bottom by the square root of x to the 6th. I just put it in the best form for each. So I did the same thing to the top and bottom there. Is that cool? So what's the top become? Divide each of these by x to the 6th. And then the same thing here. And then as x goes to negative infinity, this goes to 0. This goes to 0. So from the beginning, it really is just the ratio of the two highest degrees. But if you do this work, you'll get to the same place.
Yeah.
Now you can graph it to kind of check. And if you're right, if the real thing is square root of 4 over negative 1, so negative 2, when you graph it, you should be approaching that, and it would be approaching it from the, I don't know which way it would be approaching it, to be honest. But it should be approaching -2. So that's how you kind of check it with the graph. But don't graph me a little sketch and then give me your answer. You got to show me some work. Yeah. Anybody not get their quiz who's still here? Do I?
Is that intended?
No, I think I had here just this, and I had. No, I think that's it. Yeah. Sure. Maybe it's in here. Oh, wait. Nope. There is go to the police to get in the parking garage. They haven't lost and found over there. Although I don't know why somebody did that. What did you do that? Oh, they helped me out. So we've only talked over email, is that right? Do you have a minute to come back to the office? We have a process. So, did I forward you the emails? Oh, so you're up to date. You know the website, the syllabus, the oversheet. If you want the handouts and all this stuff before you either email me, say, could I get all the handouts so far? Or come on my office. Probably give you. You got it? Yeah. Sweet. Let me give you a copy of the quiz we took. So you can at least see what that looks like. And you got a copy of the practice test? Yeah. Oh.
And I have one question, so where
You
is it?
No, that's just so you can see what it looks like. You can try it. I can tell you how you did. The grade on the first test will also count in the place of the quiz. Yeah.
So where you send us the key?
Oh, I'll have the key next time. I'll have the key on Thursday. Yes.
So we have the test on 11, right?
A week from today, yeah.
Yeah. Okay.
Yeah.
Thank you.
Sure.